All right, so what we're looking at here, the first question you guys had to do together or by yourselves was question number 3. Zircon is often used as an imitation diamond in custom jewelry. Calculate how much the speed of light decreases when it passes from air into zircon. Now what we're doing is we're assuming air is not a perfect vacuum, and therefore it has a refractive index of 1.003, very, very close to 1, but not quite. And then zircon has a refractive index of 1.92. I'm going to do my best to remember those two numbers. That way I do not have to go back and forth here. So for question number 3, what we need to do is figure out the speed of light in air and the speed of light in zircon. So starting with air, I know n of air is 1.003. C, the speed of light in a vacuum, is 3.00 times 10 to the 8. And V then would be the speed of light in air. Okay, so what I'll do is I'll put V air. That way we know what this V represents. N equals C over V. 1.003 equals 3 times 10 to the 8 over V. And then remember your quick trick here is to simply swap those two positions. So V equals 3 times 10 to the 8 over 1.003. Now don't be intimidated by the 10 to the power of 8. That's just going to become part of your final answer. So open up our calculators and we're simply going to type in our calculator 3 divided by 1.003 and we are going to get 2.99. Wow, so much slower in air, right? That's the speed of light in air. Now we're going to do the exact same thing for zircon. N of zircon, I believe, was 1.92, and you can correct me if I'm wrong there. I tried to remember it. C, 3 times 10 to the 8, and then V in zircon is what we are searching for. So N of zircon equals C over V. And again, you don't really have to do that part, but it is good for reference. 1.92 equals 3 times 10 to the 8 over V of zircon. Again, we'll just use our quick trick here, swapping the positions, and then V of zircon is 3 times 10 to the 8 over 1.92. So 3 divided by 1.92 is 1.56. Okay, and then it simply wants to know the difference. Okay, so again, meters per second. Please don't forget your units like I did. Meters per second. Please don't forget your units like I did. And then you can just simply subtract these two numbers to figure out the difference, okay? You don't have to subtract the 10 to the power of 8. You only have to subtract the first part. 2.99 minus 1.56. That's it. And then your answer, of course, will be times 10 to the power of 8. The 10 to the power of 8 just kind of follows along. So you don't have to worry too much about that. That's it for 3. Okay, for question number 4, we want to figure out how long it's going to take for light to travel through a 1 centimeter thick piece of quartz, given that quartz has a refractive index of 1.46. So the first thing we're going to do is figure out the speed of light in quartz. So for 4, N, C, and V, again, because we're using speed, we're going to use the refractive index equation. 1.46, 3 times 10 to the 8. And we are looking for V. So just like the previous question, I'm just substituting in all my values. I'm going to use my quick trick here. V equals 3 times 10 to the 8 over 1.46. And V equals, again, my answer will be times 10 to the power of 8 meters per second. 3 divided by 1.46. So 2.05. Now, our last part of this is to figure out how long it takes for light to travel through a 1 centimeter piece of quartz. And speed is equal to distance over time. So most of the time we use V for speed. You can use S for speed, but usually we use V. Okay, so speed equals distance over time. Now, it is a 1 centimeter piece of quartz. However, our speed is in meters per second. So what we're going to do is we're going to change 1 centimeter to 0.01 meters. You do that divided by 100. So 1 centimeter is 1/100th of a meter, 0.01. So that's the number that we're going to use. So we know that the speed of light was 2.05 times 10 to the power of 8. We know that the distance traveled is 0.01 meters, and we're looking for time in seconds. Again, just like before, this is the exact same question, okay? We just simply swap spots. Now this one's tricky. T equals 0.01 over 2.05 times 10 to the power of 8. Now, this question, I know it's very difficult and there's going to be a lot of math rules in here that you might not have learned before. If you, again, had math this quad, then you might know about some exponent rules when we take a number with an exponent and we move it from the numerator to the denominator, or if we move it from the denominator to the numerator, you might have learned about the rule about how we can change the exponent to make our answer a little bit more simplified here. Or what we can do is simply on our calculator, we can simply type 0.01 divided by. Now, here's where it gets tricky. You must open a bracket because we need to divide by the full denominator. Okay? The full denominator is 2.05 times 10. Now you need to find your exponent button on your calculator. Your exponent button on your calculator is either this. It'll either be a little hat that looks like this. That's what mine is. It's right over here. Or it'll be x to the y. Most likely it'll be x to the y. Or it will be y to the x. That's least likely, but it could be that. And the least likely is x with a little box up at the top. You're looking for one of those 4 buttons. And you're typing 2.05 times 10 to the power of 8. This is going to do my calculation for me all in one step on my calculator. Now you're going to get probably a really strange answer on your calculator, and I'll show you what mine looks like. Okay, mine says 4.87804.878 E negative 11. Well, that answer is simply 4.88. The E negative 11, and on your calculator it might have a little space. And you might be like, wow, what? I've never seen a space in between my last number and then all of a sudden I got a weird number over here. What that means is whether you have an E or you might have a 10 times or you might have a little space here, what that means is times 10 to the negative 11, and time is measured in seconds. So that's how long it will take. So what that means is it's going to take 0.0000000000488 seconds, which is next to no time at all. It's going to pass through very, very quickly. Okay? So that's a little bit tricky, something you might have learned in math, something you might have learned maybe in physics, if you've had some sort of other physics course before, but this is just simply called scientific notation. It's a way of making a ridiculously large number look a little bit more simplified. Again, we'll focus on that later on if you're not quite sure how to do that. All right, we're going to move on to our last question, which is question number 5. B. Okay, so for question 5B, it gives us an incident index, an incident angle. It gives us an index of refraction for our refracted medium, and it's asking us to find a refracted angle. So when you look back at 5B, it tells you that the light ray has an angle of incidence of 30, and for part B, glass with an index of refraction of 1.51 is our incident medium because that's where the light is starting. So my incident refractive index is 1.51. 30 degrees is my incident angle. My refracted medium is 1.003, that's air, and it wants me to find the angle of refraction. Because I'm using angles, this is a Snell's law question, Ni sine theta I equals Nr sine theta R. So for this question, we sub in only numbers into these 4 variables. The signs stay around until the very end. So 1.51 sine 30 equals 1.003 sine theta R. We are searching for theta R. First step, divide both sides by the number attached to sine theta R. This will remove it, and we will slowly start to get theta R by itself. So I get 1.51 sine 30 over 1.003 equals sine theta R. Remember, that sine's not gone yet. It sticks around until I physically get rid of that. In my calculator, I'm simply going to type the left side of my equation in and simplify it. 1.51 sine 30 divided by 1.003 equals 0.7527 equals sine theta R. Now, whenever we solve for an angle, our last step is always to write sin inverse, so sine inverse 0.7527, and that removes the sine from the theta R, and now theta R is isolated. To access sine inverse on our calculator, we simply hit the second function button or the shift button, depending on the calculator that you have, and then sine. And you can see on your display, it brings up sine inverse. And we type in 0.7527. And as long as we're in degree mode, we should get the right answer. Theta R is equal to approximately 49 degrees, as we like to round it, usually to the nearest whole number. Now I can draw my accurate diagram that they were asking for. So here is the boundary between glass and air, right? glass was my incident medium, air was my refractive medium. Here's my normal, my incident ray, whoops, not sure what happened there. Incident ray is at an angle of 30 degrees. My refracted ray is 49, which means my refracted ray is actually going to go away from the normal. And of course, you can use a protractor to make this very accurate. And this is 49 degrees. So because my normal is moving, or sorry, because my refracted ray is moving away from my normal, we know that the light is speeding up.